Okay, so this is what your probability distribution looks like. Yes, you need to make it. Yes, it's a pain in the butt. The main reason is because I need you to understand the process that goes into this, what these numbers actually mean and what they represent, right? This number 7 is the probability of you getting a 7 is pretty higher than any of the other probabilities, and that it's what we call normally distributed, which you'll learn by the end of this term, by the end of this unit, is that it's grouped like a bell curve, where most of your probabilities are grouped in the center with like deteriorating probabilities out to the end. So it's just so important that you understand this fully. And so I know it's a pain in the butt now, but it's to help you connect with this process at a later time. So find the probability that x is less than or equal to 4. It's just the probability that x is equal to 0 plus the probability that x is equal to 1 plus the probability that x is equal to 2 plus the probability that x is equal to 4, right? In other words, probability that x equals 0 is 0 because you can't get 0 when you're rolling. And also the probability that x equals 1 is 0. And this is x equals 3, and then x equals 4. My bad. So probability x equals 2 is 1 over 36, plus the probability that x equals 3 is 2 out of 36. Probability that x equals 4 is 3 out of 36. That's 6 out of 36, which is 1/6, which is equal to 0.167. Okay. So then the probability that x is greater than or equal to 6, that's the probability that x is equal to 6, which is 5 out of 36. And I know I'm going to be adding them all together over 36, right? So 5 over 36, x equals 7 would be 6, 5, 4, 3, 2, 1. Right? Just adding up all of these probabilities. So then that's going to be 5 and 5 is 10, 6 and 4 is another 10 to make 20. 20 plus 6 is 26, which is 13 over 18, which is 0.722. All of those are acceptable, right? As long as it's a fraction or a decimal, not as a percent. Okay, last example for today. Hopefully all of this makes sense. It's kind of clicking in with things that you already know about probability and already know about statistics. I didn't really explain this because I'm just grabbing the probabilities that they are either 2, 3, or 4. Either or means plus, right? The probability of x equals 6 and something else would not be possible because you're only talking about one outcome, but then you would be multiplying. Okay, last one. Radon is a major cause of lung cancer. It's a radioactive gas produced by the natural decay of radium in rocks that contain small amounts of uranium. Studies in area with high levels of radon revealed that 1/3 of the houses in these areas have a dangerous level of, I think I got stopped when I was typing this and retyped it. I'm sure that's happened to you before. I once started typing a dream. I once fell asleep while I was typing an essay in high school in IB, and I fell asleep, and I remember I woke up and I read what I had typed, and it was like a few sentences of the dream that I was having. It was very strange. Okay, so studies in an area with high levels of radon revealed that 1/3 of the houses in this area have dangerous levels of this gas. Suppose that 2 houses are randomly selected, and we define the random variable x to be the number of houses with dangerous levels. Find the probability distribution of x by a table and a graph. So questions like this, I think, can really freak people out because they're wondering how this is a math problem. There are not any numbers. And this is a math problem because we're talking about all of the possibilities. We're talking about the entire sample size of what's going on here. I wanted to visually understand this first, which I think a lot of you guys do. And I first thought, hey, I think I can draw a tree diagram to represent this. And your textbook doesn't. Your textbook does not draw a tree diagram to represent it, but you absolutely could. And so I wanted to see maybe some of you needed to have a visual representation as well. I'm going to have DL be dangerous levels. It's like the danger zone, but as a level. So my first house can have dangerous levels or not dangerous levels. And then my second house could then also have dangerous levels and not dangerous levels. So this first bracket is house 1, and the second bracket is house 2. So the probability of having dangerous levels is stated up here in the top. It says studies in area with high levels of radon revealed that 1/3 of houses in these areas have dangerous levels. So a dangerous level probability is 1/3, which means a not dangerous level would be 2/3. 1/3, 2/3 makes 1, right? Remember that we always have to add up to 1. And then I continue these probabilities over here. This is still 1/3, this is 2/3, this is still 1/3, and this is still 2/3. So the probability that the first house has dangerous levels and then the second house has dangerous levels is 1/3 times 1/3, which is 1/9. The probability of the first one having dangerous levels and then the second one not having dangerous levels is 1/3 times 2/3, which is 2/9. 2/3, 1/3, 2/9, 2/3, 2/3, 4/9. And we've broken it down now into probabilities. The probability that we have 0 houses with dangerous levels is 4/9, versus the probability of having 1 house with dangerous levels is either this path of 2/9 or this path of 2/9. You have 2 parts on this tree diagram that have 1 house with dangerous levels. And then you only have 1 part that has 2 houses with dangerous levels, that both of them have dangerous levels, is here. So the probability distribution here as a table versus a graph is talking about the number of houses with dangerous levels. So you can have 0, 1, or 2 houses with dangerous levels. So houses with dangerous levels. And then the probability. So you can have 0 houses, 1 houses, or 1 house, or 2 houses. Keep in mind, 0 houses with dangerous levels is 4/9. 2 houses, both of them having dangerous levels, is 1/9. One of them could either be that the first one has dangerous levels and the second one does not, or the second one had first one did not have dangerous levels and the second one did. So it's both of those probabilities together, either or. So we have to add them, and that's 2/9 plus 2/9, which is 4/9. Again, so the probability that one of them has dangerous levels is equal to the probability that none of them have dangerous levels, which I think is interesting. That if you and your neighbor are being tested for dangerous levels of radon, there's an equal level probability that one of you has it versus none of you having it. So that's an interesting way of looking at it. So that's it represented as a table. I would not have been able to get to this conclusion without first drawing a tree diagram to kind of like understand the relationship. So that's why it was helpful for me to do that. So keep in mind those little shortcuts that can help visually represent these situations to you. I need to still represent it as a graph, which is that histogram, the bar graph guy. So I have 0 houses, 1 house, 2 houses, and then we're going up on nights. 1, 2, 3, 4, 5, 6. So this is 1/9, 2/9, 3/9, 4/9. So 0 is 4/9 and 1. Right? Both of these are 4/9, and then 2 is 1/9. And that is your probability distribution. I should be labeling my axes, houses, and then probability. Okay, so that's pretty much all I wanted you to get away from this, is how to take a sample set and their probabilities and then turn it into a table and then turn it into a histogram. And so then we're going to talk about how these histograms have different types of distributions for this entire unit. So you can have something that's normally distributed, and you can have something that's called binomially or It's called a binomial distribution. So right now we're just kind of building up your familiarity with representing data in this way, but it's taking things that you already know and representing it in a somewhat familiar way, but just kind of slightly changing it. Good job.